Hello, and welcome to the Chapter 16.1 lecture on double integrals over rectangular regions. Calc 1, when you first learned definite integrals, you learned Riemann sums and breaking up the area into a sum of approximating rectangles. Well, the same thing applies in the Calculus 3 context. Given a surface, we can approximate the volume underneath it with rectangular solids, which are just the three-dimensional analog of Riemann rectangles. And as the widths of these rectangular solids approaches zero, then we'll have a better and better approximation to the area as we sum those up. So here's that rigorous definition for double integrals. So a function f defined on a rectangular region is integrable if the limit as delta approaches zero of the sum of the height of the rectangle times its base exists for all partitions of that region. A partition being no matter how we divide it up, so long as the widths go to zero, and we can choose any point inside of each rectangle for the value at which we evaluate the height. And that limit, if it exists, is called the double integral of f over the region, and we denote it with this double integral sign, the double integral of f over the region R, dA. dA for area, the area, and that's a two-dimensional region R. And we can find these volumetric Riemann sums, double integrals, via slicing. So this is very similar to what you did near the end of Calc 2, when you were evaluating volumes by finding cylindrical slices, for example. We can do the same thing, same idea, where to find the volume underneath a surface, we can evaluate the area of a single slice, say at a given x value, and then add up each of those cross-sectional areas, dx in this case, and that will give us a little volume, and then we can integrate and add together all of those little volumes. So let's do an example. Let's find the volume underneath this plane, z equals 6 minus 2x minus y, over the region in quadrant 1, bound by x equals 1 and y equals 2. Okay, so we can first find this area, the area A of y, at a given y underneath the plane. And what would that be? So we're holding y constant and integrating from x equals 0 to x equals 1 of the height. So we're holding y constant here, and the integral of this, dx, that will be 6x minus x squared minus xy, evaluated between x equals 0 and x equals 1. Yes, so because we are holding y constant here, this is really the inverse of the partial derivative del x. And technically, there's also that plus a constant. And in this case, that constant would be plus c of y, since y is constant. But it cancels out in the definite integral, so we never have to write it in the same way that we never wrote it in Calculus 2. Okay, so evaluating that difference, we wind up with 5 minus y. After all evaluating that difference, we just plug in 1, we plug in 0, and take the difference, and you can see that we have 6 minus 1 is 5 minus y, minus 0, we get the 5 minus y. So we have established that this red area here is 5 minus y at a given y value. And now what we can do is integrate that a of y that we just found, dy, to add together all of those cross-sectional areas, dy, to give it a little tiny volume, and add all of those together, and we'll get the total volume underneath the plane. So, in other words, the volume is the integral from 0 to 2 of a of y dy. And notice that because a of y itself was this, we wind up with literally a double integral for evaluating this volume. And we already evaluated that inside integral. It was the 5 minus y that we found. And I want you to imagine this dy here as it follows. We have a little difference dy, and imagine that little difference dy gives it a tiny volume. So what we're really doing here is considering this area times dy, that's like a base times a height, and we have this little tiny volumetric slice, and then in evaluating this integral, we're adding together all of those little tiny volumes to get the total volume. Okay, and that integral is 5y minus 1/2 y squared, and we're evaluating that between y equals 0 and y equals 2, and we wind up with 8. So that is evaluating a double integral, is what we really just did, except we did it through breaking it down into these steps where we first considered this area by itself, just to help gain a geometric understanding of what we were doing. But in the future, moving forward, we'll just immediately write down a double integral like this. And when we look at that, we'll be able to see that the inside guy is the a of y. Okay, now let's do an example of computing a double integral, finding the volume underneath a surface. So this will be very similar to the example that we did just over here, except that now we'll be kind of doing it from scratch. And we'll see how to think about it. So let's find the volume underneath the surface z equals 4x plus 2y between x equals 0 and 2 and y between 0 and 3 by slicing parallel to the y-axis. So let's visualize what's happening. So in my head, I think of this kind of picture. We have some shaped surface above this rectangular region given by x is between 0 and 2 and y is between 0 and 3. And we want to find the volume underneath this purple function above this blue rectangle. And it tells us that we specifically want to do it, in this case, by slicing parallel to the y-axis. So let's visualize that. Here's the y-axis, and parallel to the y-axis would be like this for the base of one of our slices, and then our slice would go up to our surface up here. Okay, so the area of this would be our, okay, would it be a of x or a of y? Okay, so we're holding x constant in this case. To be parallel to the y-axis, we're holding x constant. So this would be our a of x. Okay, so the volume that we want to find, so that's the double integral over r of 4x plus 2y dr in one notation. And in this case, we're holding x constant and first integrating with respect to y. And that will find us the area of this slice. So because our inner function, the thing that we're first doing, is integrating with respect to y, there will be a dy here. Okay, and this guy is our a of x, integral as y moves from 0 up to what? Up to 3. Perhaps I should color code that. That's y equals 0 up to y equals 3. Okay, and then once we find that area a of x, of that yellow guy, then we will want to add together all of those little areas, dx, to give each area a little tiny volume, and add together all of those between x equals 0 up to x equals 2. Okay, so up to x equals 2. And we'll be doing that dx. So our outer guy is dx, and we're integrating between x equals 0 up to x equals 2. And that is how you form a double integral with the appropriate bounds, through visualizing the slicing. And in this case, it told us to slice parallel to the y-axis. We could have also sliced parallel to the x-axis. And in fact, I think we'll be doing that right here. So after this, we're going to illustrate doing the exact same integral with a different slicing method, and that will swap our dx and dy. Okay, but with this slicing method, it's done that way. And then we can evaluate that. And we always evaluate these guys going from the inside out. Okay, so the inside integral, that's dy. That means we're holding x constant. So that will be 4xy plus y squared evaluated between y equals 0 and y equals 3 dx. Okay, and again, this whole inner guy is still our a of x. Okay, and evaluating this at y equals 0, clearly both of these guys are 0, and at y equals 3, this is 12x plus 9, and then subtracting the y equals 0 part subtracts nothing, so we just have that dx. Okay, and this guy is that same a of x that was on the inside. Okay, so we found that at a given x, the area of this yellow slice here is 12x plus 9. So it's clearly increasing as x increases, and that indicates that, well, as x increases, the height is getting higher. And that's exactly what the formula tells us in the first place. So that's good. It checks out. It passes the make sense test. Okay, now we can keep going. At this point, it's just an ordinary Calc 1 integral. And that is 6x squared plus 9x evaluated between 0 and 2. And we get 42 is the volume. Okay, now for the sake of illustration, let's do this exact same problem, except now we'll do it by first slicing parallel to the x-axis. And we should get the same answer. It shouldn't matter which way we slice because it will still be doing the same volumetric integral. Okay, so same formula. Now we're slicing parallel to the x-axis. Okay, so we still want the double integral over this region R of 4x plus 2y dr. And now we want to slice parallel to the x-axis. Okay, so parallel to the x-axis, what would that look like? So then that one of our slices would look like this, and it would extend up to the surface. So that would be our slice A of what? Well, now it's a function of y. So at a given y, then we'll have this cross-sectional area. Okay, so our inner integral will be that cross-sectional area A of y. And what is that? Well, it goes from x equals 0 up to x equals 2 because of these bounds. So that'll be from 0 to 2 of the height d what? Well, dx, because x is what's varying here. We're holding y constant. And then we're going to let this cross-sectional slice move from y equals 0 up to y equals 3, adding together all of those little tiny slice volumes, dy. So y equals 0 to y equals 3 of those slices dy. So that would be our setup for this way. Now take a look at this integral. This is dx dy. It should get the same volume. It's still the same double integral. And in the previous way, it was dy dx with these slices. Look at this slice versus this one. And slicing this way, it was dy dx. And notice that the bounds are also swapped. This was 0 to 2, 0 to 3, dy dx. Slicing this way is 0 to 3, 0 to 2, dx dy. And now we evaluate this. Okay, that inner integral is this, integrating with respect to x, regarding y as a constant, which it is in this anti-partial derivative. And evaluating that, we get 8 plus 4y. Okay, so at a given y, the area of this is 8 plus 4y. And now we add together all of those areas dy, and lo and behold, we get the same 42 as we got slicing the other way. So in this case, we had a choice ultimately of which way we sliced. It came down to a matter of preference, and both ways were equally good. As we move forward, we'll see that in some cases, slicing one way will yield something easy to compute, while slicing the other way will be much more difficult to compute, and we'll see how to decide which way to do it. So go ahead and try your hand at this problem. In this case, don't worry, it doesn't matter which way you slice. You can do whichever way you prefer and see if you can compute this double integral. Okay, so no matter how you sliced it, you should have gotten an answer of 0. Before we see geometrically why that's true, let's do this. Okay, so from the previous 2 examples, maybe we can see at this point that if we slice, say, dx dy, okay, this would be our a of y. And at a given fixed y, x moves between -1 and 1. We're doing this to the function z equals xy. And then we integrate those slices dy from y equals 0 to 1. Okay, or you could have done it this way, slicing the other way. So evaluating this, integral of xy dx is 1/2 x squared y from x equals -1 to 1. However, that is the integral of 0 dy, so we wind up with 0. And doing it the other way, other slicing, we have 1/2 xy squared when we integrate dy from y equals 0 to 1. And that is 1/2 x evaluated between -1 and 1 dx. And that is also 0. Okay, good. They agree, as they should. But why are they 0? How can the area or volume in this case underneath it be 0? Well, it's in the same way that, say, the integral from 0 to 2 pi of sine x dx back in Calc 1 was 0 because sine oscillated. And you could have such a thing as negative area, essentially, if you're below the x-axis. So the same thing applies here. If we're below the xy plane, then we have negative area. And the graph of z equals xy looks like this. So x from -1 to 1 and y from 0 to 1. We had a region that looked like this. And you can see that the positive volume there looks like it cancels out with the negative volume there due to symmetry. Okay, now, in both of the examples that we have done, we saw and perhaps intuitively garnered that it does not matter in which order, well, we slice, and that's always true, but also specifically for rectangular regions. When we switch which way we're slicing, all that happened was that we switched the bounds. So slicing this way, it was 0 to 2 and then 0 to 3, dx dy. While slicing this way, it was 0 to 3, 0 to 2, dy dx. So those guys just got swapped. And that's exactly what Fubini's theorem says. It says that if we are over a rectangular region R, or x between 0 and b and y between c and d, then the double integral, that will be the integral from a to b dx, the bound along x, and then from c to d dy, bound along y. Or we can swap the two, and then these bounds just get swapped. C to d along y, and then a to b along x. And Fubini's theorem is kind of an inverse of Clairaut's theorem. Remember that Clairaut's theorem says that it does not matter in which order you do the partial derivatives. Well, here it's saying that over a rectangular region, it does not matter in which order you do the partial integration. And I want to point out, this is for rectangular regions. In a bit, we'll be having double integrals that involve non-constants here. Might look like this, for example. And in this case, it would be not rectangular. You have a non-constant bound, and then this theorem does not apply. It applies only with constant bounds. So here's just another picture of the kind of thing that we've been doing. We have this shape. We want to find the volume underneath. Over this region, it does not matter if we slice this way or that way. And in slicing one way or the other, all that happens is that we swap the bounds on the two integrals, and also swap the dx dy for dy dx, depending upon which way we're slicing. And lastly, on Fubini's theorem, which says that you can swap the order of integration, that doesn't mean that both orders are equally convenient. And you'll want to choose a convenient order of integration. And one way to do this is to kind of look ahead. So let's say we want to take the double integral of y e to the xy dA over some region. And if we were to take it dy dx, then we would be integrating y e to the xy dy, and that would require integration by parts, because that's a product of two things, both of which have a y in them. On the other hand, if we were to take it dx dy, then doing the inside integral is quite simple because there's just a single x, and then when we integrate that dy, there's also no integration by parts. So the point is that if one order of integration is messy, try the other order of integration, it might be much nicer. So take a look at this. If you wanted to integrate x times sine of xy over a rectangular region, what do you think you should do? Integrate dx dy or dy dx? Well, looking ahead, if we were to integrate this dx dy, then our inner integral would be an integral of two things, both with an x, that's integration by parts. While if we were to integrate dy dx, then we have a much simpler integral. Now x is just a constant relative to y, and we can undo the chain rule, and the integral of that would be quite directly negative cosine xy. Okay, and one last little thing, we can talk about the average value of a function. So the volume of some region is the area of the base times the average height. That makes sense. Volume is base times height. And then if we take this and solve for the average height by just dividing both sides by the area of the base, we wind up with this. Okay, all we're doing is dividing both sides by the area of the base. And this gives us a formula for the average value, average height of an integrable function is 1 over the area of the base times the total volume. Yep, again, because volume is base times average height. So for example, in this example that we already did, we found that the total volume was 8, and the area of the base here is 1 times 2 is 2. So the average value of this function is 1 over the area of the base, 1/2, times that volume, that's 1/2 times 8, is 4. And that concludes our 16.1 lecture. Have a great one.